Convolutional neural networks. Please shut your laptops, all the usual good stuff. You'll notice something conspicuous by its absence. I don't have my trident today. So I'm going to have to use the laser pointer to point. Those of you on Zoom may not be able to see the pointer. If that is the case, please let me know. So today's lecture is going to begin with a story on cats. And what do cats have to do with convolutional neural networks? It has to do with human vision. So for the longest time, we've tried to figure out how it is that we actually visually perceive the world. What is the set of processes within our head that allows us to see things and allows us to interpret whatever signals we get through our eyes? And much of early research was based on this concept of Gestalt, where we assume that we sort of compose things out of parts. So look at these pictures. The picture to the top left. What do you see? Anyone? It looks like a cube, but is it really a cube? No, right? It's just a bunch of Pac-Man looking things. What about the next one? It's not really a dog, right? And my favorite one is the one to the extreme right. What do you see? A mine? You see how many of you see a sphere with spikes in it? All of you do, right? And there is no sphere. So what your brain did was to fill in things and imagine stuff that wasn't there. And believe it or not, pretty much all of your vision is essentially just you imagining things. Almost certainly none of what you think you saw was actually here. So, including me. Now, this sort of gives us an idea of how things, the bigger picture of how we perceive, but what's the cognitive process that goes on inside? Nobody really knew until these two guys, Hubel and Wiesel in 1959. And this is where cats come in. They did the first study on the neural correlates of vision, the receptive fields of the cat's striate cortex. The cat's striate cortex is the equivalent in the humans of the V1 cortex. And again, I like to use human vision as an example of why we are brilliantly bad design. Firstly, your eyes are all inverted. Your nerves are outside the retina. So they have to punch a hole through the retina to go inside. And now if I, as an engineer, were to build an eye, I would have the sensor and the wires behind the sensor, not in front of the sensor. But that's not how our eye is built. You have the wires in front of the sensor. It has to punch a hole through the sensor, which is why we have a blind spot. But then I, as an engineer, if I were to build a robot, the wire that went out from the camera is going to just attach to the closest portion of the processor behind it. That's not what happens in your brain. Those things go all the way to the back of your head. And that's where your V1 cortex is. And then the signals flow back forward as you make more and more interpretations of what you see. So brilliantly bad design, right? That's an oxymoron, isn't it? So, and well, the cat's striate cortex is the equivalent of the V1 cortex, which is right at the back of our head. These guys got a hold of 24 cats. They don't exactly tell us where they got the cats from. So they anesthetized the cats with truth serum, held their eyes open, and beamed light into it. They don't tell us if the cats actually survived the experiment, but then they do allude to the fact that the brain tissue was studied afterwards. So they leave that to our imagination, I suppose. Now, what exactly did they do? They held the eyes open, and then they beamed lights of different wavelengths, basically a dot, and they moved it in different directions to see how the eye responded. And here's what they found. And this defines the immediate 20 millisecond response of the retinal cells. What is it the eye senses immediately, right? And here's what they found. There's a lot of text on the slide, but the general picture is this. If you move the point of light in some directions, the individual cells at the back of your head light up. In other directions, they do not. Specifically, they found that any individual cell in your V1 in the striate V1 cortex doesn't respond to every point on the retina. It responds only to signals on a small portion of the retina. Much of it is ignored. Even in that region of the retina, there are certain regions shown by these red dots over here, where if there's any light incident on it, that cell will never fire. So these are inhibitory regions. And then there are regions shown in blue where if there is light, the cell does fire, provided there is no light on the red regions. So if you have a uniform, if you have a uniform field of light falling on every portion of the retina, then the portion that falls on the red cells is going to cancel out the portion that falls on the blue cells. But if you just have a single dot, which avoids the red regions and falls on the blue regions, the cell fires. So basically, it turns out that every one of these cells has what they call a receptive field, how it responds, which looks like this. They are oriented patterns of light. So each cell in the V1 cortex or the striate cortex responds to linear patterns of light. And so here's one of their experiments. The arrow to the left, the line to the left shows the direction in which the beam of light was moved. And the figure and these figures show the response of the neurons. And in this particular case, when the beam is moved left and right, you see there's no response. As you keep increasing the angle, by the time it comes up to 90 degrees, the neuron is really responding. But then as you continue further, eventually it stops responding. So this was a neuron which responds to vertical patterns of light. And so here is what they found. Oriented slits of light were the most effective stimuli for activating the striate cortex neurons. Now, observe these patterns. We're going to see them again a couple of times in the next couple of days. So in a later paper, they also showed that within the striate cortex, there are two levels of processing. It turns out that it's not just a simple response to a stimulus. Exactly why do we have this kind of response? It has to do with how the neurons themselves are connected. So each neuron in the V1 cortex is connected to linear patterns of cells in the retina. Each cell in the retina, of course, has an isotropic, almost isotropic response, kind of circular. But then if you connect up to a line of these guys, then you're going to respond to linear patterns of light. And so this is what they call the S cells. Each S cell responded to a linear pattern of light oriented in a specific direction. But then there were other cells. The S cells tended to be very easily fooled by noise. You have some diffuse light, you have other kinds of garbage, they fire. And so you had something called C cells, where C stands for complex, S stands for simple. And the complex cells would read in bunches of S cell responses and only pick up the largest of these. And here the point was that the C cells, the complex cells, seem to be cleaning up the response of the S cells to eliminate any kind of incidental firing by the S cells. So they have a robust response. And they also showed that the responses in the cortex kind of build up. So you have the first level of S cells, which respond to stimuli on the retina. Then you have the C cells, which clean up the S cells. Then you have a second set of S cells, which read the responses of the C cells that cleaned up the previous response. And then they have their own C cells and so on. And as you go through these layers of S and C cells, the kind of patterns that the brain responds to become more and more complex. So the first layer maybe just responds to linear oriented patterns of light. But then the next layer builds up more complex patterns, and then the next layer builds up more complex patterns, and so on. So eventually, of course, they graduated from working with cats, which is bad enough, to working with monkeys. So I won't follow that line of research anymore. But then let's get back to computer science. We have by now, by 1959 or 1962, some idea of how the human brain, or at least the cat cortex, responds to visual stimuli. And of course, this is adding insult to injury. They said the model cannot accommodate color, spatial frequency, and many other features, kind of invalidating their own torture of cats. But first, there's a point. Okay, Angel, can you tell me the answer? 1, right. So the S cells find patterns and C cells clean them up. Easy enough, right? Now, fast forward 21 years, 1980, Kunihiko Fukushima. Now, this is Kunihiko Fukushima, but this was not Kunihiko Fukushima in 1980. I just found a picture of him at some point, taken at some point in his life on the web. Now, he tried to computationalize the Hubel and Wiesel model. And in doing so, he realized that the basic model, so this is now your first computational model of vision, but then Fukushima found that there's something missing in how they describe things. How many of you have heard of the Jennifer Aniston neuron? You have. Can you tell us what it is?
I don't remember.
Okay. So it turns out that some people have this thing called the Jennifer Aniston neuron. It's a neuron in their head that responds only to Jennifer Aniston. So people who have epilepsy, they tend to be fantastic subjects for cognitive neuroscientists because they have to get their heads opened and the lesions are treated. So they'd be lying there with their skull open in the hospital for a few days. And these guys come along, easy subjects. They put a mesh of sensors on their head and show them various things and make them guinea pigs. And they found on one particular subject that there was a neuron that only fired anytime this person was shown a picture of Jennifer Aniston. There was a paper in Nature or Science about it. That's the famous Jennifer Aniston neuron. Now, there's nothing special about Jennifer Aniston. It's not as if she's such a special person that each of us has evolutionarily developed one specific neuron just to detect her. It's just that we have neurons dedicated to specific objects, specific people, the famous grandmother cell. Many of us have a grandmother cell in our head, which will respond anytime we see our grandma. Except they're going to respond regardless of where grandma is in the field of vision. It doesn't matter whether she's to the right or to the left or in the center. There is position invariance. And Hubel and Wiesel's model doesn't actually capture this positional invariance. So Fukushima came up with this model, which he called a neocognitron. The fact that it's called the neocognitron tells me that there must have been a previous model called the cognitron, but I have no idea what it was. I do know what the neocognitron is. It consisted of blocks, a sequence of blocks. Within each block, there were two subcomponents. One was a layer of what they call S cells, modeled after Hubel and Wiesel simple cells. And one was a layer of what they call C cells, modeled after Hubel and Wiesel's C cells. S cells respond to signals from the previous block, from the previous layer, because each block had a layer. And C cells, just like in the cat striate cortex, clean up the response of the S cells. And so here's how it is, the way it worked. Firstly, within each block had one structure which they call the S, but the S itself consisted of several planes, each corresponding to one pattern that this block could detect. And so within each plane, you had many neurons arranged like so in a grid. And the specialty over here is that every one of these neurons responded in exactly the same way. So if you consider the very first block of this model, this very first block is going to be looking at the pictures. And here's grandma. And this block is going to, this cell over here may be looking here, this cell may be looking here, this cell may be looking here, and this cell looks at grandma, so it's going to fire. But then the point is, because all of them have the same response, it doesn't matter where grandma is in the picture, that's some cell in this plane is going to fire. And so you have several such planes, each one detecting a different pattern. And then corresponding to each S plane, there was a C plane. The C plane is also a grid of cells. And each cell over here looks at a small region of responses in the corresponding S plane and cleans it up. It performs some kind of a majority vote or a highest value vote to respond. So the C cells clean up the responses of the S cells, and the S cells respond to what happened earlier. Now, after this, there would be a second block of the same kind. So this is S and this is C. And now over here, you would have several C cell planes, one corresponding to each S cell over here. And then the next S cell block is again going to have several planes, also with a grid of responses, grid of neurons. And now each neuron over here is going to simultaneously look at exactly the same region of each of the C planes from the previous block. This looked familiar from the last class. This looks a lot like what we were doing with our CNNs, right? And so each of these, now again, you have a bunch of cells over here, all with identical response. This might again be doing the same thing and so on. And then corresponding to each of these S cells is a C, S planes is a C plane where each cell sort of cleans up the response in a small region of the corresponding S plane. And because the C planes were cleaning up stuff, they're looking at groups of neurons. The C planes are smaller than the S planes. And so as you go deeper and deeper into the network, like so, you get the C planes keep getting smaller and smaller and smaller, so do the S planes, but the number of planes keeps increasing. And how exactly do the S and the C planes respond? The C planes are the so-called complex cell planes. They do not have a learnable response. They have a fixed response. They just respond to, this is what the model is born with. The S planes are the only ones which have plastic cells, things that can learn to respond. They have parameters which can be trained. And so as you go through the model, the first layer cells are going to recognize simple patterns. The second layer cells are beginning to compose the patterns from the first layer. The third block composes patterns from the second block, and so on. As you go through the blocks, you expect the patterns that each block recognizes to be increasingly complex. Now, they actually came up with formulae for how the S cell and the C cell responds. The formulae are ugly. There's no reason for us to know what these formulae are. There's no reason for us to understand them, because if you take a step back and look at them, the first one, the S cell responses look like a ReLU. The C cell response also looks a bit like a ReLU, but if you look even closer, it just looks like a max. And so you have an S cell which computes a weighted sum of all of these guys. So this S cell over here is going to compute a weighted sum of all of these terms, and then apply a ReLU activation to it. The C cell is going to look at a bunch of stuff over here and just pick up the maximum value. That's a
Professor,
process.
could you let us know why the size decreases across the layers?
Because when you have an S pattern of this S cell of this kind, then if a C cell over here looks at this region, the next C cell doesn't have to look at any of the cells within this region. All of these are supposedly capturing the same pattern. It's just picking up the largest one. Does that answer your question?
Okay, thanks, Professor.
Right. So, and well, how do you train this model? They trained the model. So again, the deeper the layer, the larger the receptive field of each neuron, because you're seeing larger and larger regions of the input. And so the C planes get smaller with layer number, and the number of these planes, the number of these planes increase, right? And how did they actually train it? Again, there's a lot of math on the slide. We can skip it, but it's just simple Hebbian learning. So let's say I have a C cell from the layer L-1, then this C cell is going to feed some S cell in every one of the S planes in the next layer. So if this is in position, say, ij, then this one would be feeding, the KL position of every one of these guys. So they would just look at which of these. So anytime this got activated, they'd find which of these had the largest activation. And they'd say, okay, this guy has the largest activation, so I'm going to associate this C cell with this one here. And then you can just use Hebbian learning to increase this weight. But once you increase that weight, because all of these cells have the same response, you're also going to increase the weight of this guy here, and so on, and you would redistribute the update across all the cells in the plane. And eventually, of course, all of them get learned. Again, there's no reason for us to get into the details of it. It's just conveying the idea of what the model was really like and what it learns. Observe that the entire learning process is now completely unsupervised. All you do is provide stimuli, and you're going to use Hebbian learning to learn the weights, meaning anytime a C cell causes an S cell to activate, you increase the weight, and then you share the weight across all the cells in the plane, and that's about it. And if you keep providing it with the same pattern over and over again, they found that the cells in the early layers would learn, for instance, if you provided lots of pictures of A, the early cell layers might learn components of A. The next cell layers, the next layer block would learn more complex patterns with substructures of A. By the time you got to the final layer, you'd find that the cells fire only when you actually get an entire A in the picture. And so they actually ran these experiments. They used all of these digit pictures to train the model. And they find that eventually when you get through the layers, it turns out that each of the planes in the final layer responds to a specific kind of pattern. There is no supervision over here. All you're doing is providing pictures. And it turns out that it automatically learns to detect semantic concepts. Maybe there's one cell which only fires anytime it sees a zero. There's another plane which only fires anytime it sees a one, and so on. So the model actually manages to capture the kind of semantic structures that we actually perceive in the world with no training, with no supervision whatsoever. So this is great, right? We have a model which kind of explains how vision or visual concepts might be formed. But the reality is, in the real world, we would like to have some supervision. So okay, Theo, the first statement.
I think it's true.
You think it's true? How many of you think the first statement's true? Raise your hands, right? What about the second one? Also true. I could add supervision. So how would I add supervision to this? Anybody? How would I add supervision to this model?
Set a label for the cluster.
But then these are unsupervised guys, right? So what more do I need to do? Thank you. So I can just feed all of these into a classification neuron. One more layer, a softmax, out comes something. I have a label. I provide pictures. I provide inputs and the corresponding label, and then I can just train the network, right? And voila, you have a convolutional neural network. And so the neocognitron is fully unsupervised. Semantic labels were automatically learned. This was in the early 1980s. But then people began figuring that, we could probably add external supervision to it. And there was a lot of work on it. We had Homo Atlas and Marx in 1988. We had Kevin Lang's thesis in 1989 in CMU. So in fact, the earliest CNN models were from CMU. And these guys actually got an IEEE award for their work. But then, Jan LeCun, I think, did his work slightly after these guys. The difference between what Jan did and what these guys did was Atlas and Kevin worked on speech and Jan worked on images. So how do you add supervision? You just pass the final layer outputs through a softmax. You get a probabilistic outcome. You can compare that outcome to some target label. You get a divergence. You can back propagate this divergence, and you can learn all the parameters. Now remember, we are still using Fukushima's model, and Fukushima's model is still based on Hubel and Wiesel's 1959 model of mammalian vision, okay? So how exactly do you implement this? Yes, we're going to have the S-planes and the C-planes, except in the original model that Fukushima had, each of them had an elliptical receptive field. This is going to be hard computationally, so we will use square receptive fields. So each neuron is going to look at a square region of the plane behind it, right? So the receptive field of an S layer, S cells might be KL cross KL, of a C cell would be some, L, uppercase L, lowercase L, times the same value. Anyway, so the C cells, because of this behavior over here, that each C cell is looking at a bunch of S cells, and so you can think of these things as already having been dealt with. The next C cell is going to look at a region which doesn't quite overlap significantly with this region. And so the C planes keep getting smaller and smaller. So this is why the C planes were also thought of as performing downsampling of the input. Okay? And how exactly do they respond? The C cells, they have no learnable component. All they do is they pick the largest of the values that they look at. In the case of the S cells, first they compute an affine combination, an affine function of all of the inputs they're looking at. So this guy, for instance, might compute an affine function of all of these inputs. So that's the first affine value, and then an activation function is applied to it. The activation function is typically in LeCun's original work, it was a sigmoid. These days we'd use a ReLU, right? And also, now because this S cell has many elements, all of which have identical response, you don't need to actually create a network with so many identical neurons. Instead, you could have one neuron which just scans, which goes back to what we were discussing in the last class. Scanning, convolution is the same as scanning with an MLP, right? And so here was Jan LeCun's original work. This was in the late 80s, early 90s. The MNIST corpus was one of the big corpus of those days. This came from the US Postal Service. Back in the day, people actually wrote letters. They stuck them into actual envelopes. They wrote actual addresses on these envelopes, and they dropped them in actual post boxes. Are you familiar with any of these terms? No, right? The modern generation, you don't know what these things look like. But anyway, so, and the post office, which is an independent branch of the US government, by the way, that would get millions and millions of these letters every day, and somebody had to scan these things to find where it was supposed to go. And I don't know about you, but my handwriting is terrible. When I write a number down, I can't read it myself. And these poor fellows had to do it, and they were immensely accurate. But then they wanted to automate it. And so there was this project in the offing on trying to automatically recognize handwritten digits. And LeCun's network was one of the first to actually do such a good job that the Postal Service actually tried using it. So here's the demo that he put up back in the day, right? He called it LeNet because, he's LeCun, right? Now, so here's the story so far. The mammalian visual cortex consists of S cells which capture oriented visual patterns, and C cells which perform a majority vote, or actually a maximality vote, over groups of S cells for robustness to noise and positional jitter. The neocognitron emulates this behavior with planar banks of S and C cells with identical response to enable position invariance. Only the S cell parameters are learned, the C cells are fixed. And unsupervised learning of this network results in learning useful semantic concepts. LeCun's LeNet added external supervision to this neocognitron, where now S planes of cells with identical response are modeled by a scan, i.e. a convolution, and C planes are emulated by cells that perform a max over groups of S cells, reducing the size of the S planes. This gives us a convolutional neural network that we've already seen. So this is where, when CNNs were first proposed, they did not actually come from the perspective that I presented in the previous class. They came from here. as models of mammalian vision. So what does the CNN look like? This is what it looks like. It's got convolutional and pooling layers. Convolutional layers comprise neurons that scan their input for patterns. This correspond to S-planes. Pooling layers perform max operations on groups of output from the convolution layers. So they can correspond to C-planes, and they two may occur in any sequence, but typically they alternate. And eventually the final layer of the sequence is followed or was followed in LeCun's original network and still continues to be doing. So therefore the output of the final layer is flattened and it's passed through an MLP of some kind for the final decision. Yes.
Professor, theoretically, why does a pooling layer improve the results?
Theoretically, I can't answer any theory about this particular operation. It's just an activation as far as I'm concerned. So these days, we don't even really use pooling layers. So I don't know if there's a strong theory behind this. This actually started off as a model of mammalian vision. Okay. So maybe that's not the satisfying answer you wanted, but that's the best I've got. So here's what the network looks like. It's got convolution layers. It's got pooling layers. Only the convolution layers are learnable. The pooling layers are not. So what is this convolution layer? Let's first take a look at it. So the convolution layer is got this bunch of planes. Each plane is basically obtained by scanning the previous inputs with a single neuron, as we saw. And so this neuron is simultaneously going to be looking at all of the planes in the previous layer, as we also visualized, right? So this neuron over here is going to be simultaneously looking at all of these guys. And what happens within an individual plane? There's a two-step process. First, you compute an affine function of all the inputs. Then you apply an activation to it. So each of those plane actually has two subcomponents. The first is an affine map obtained by convolution over the maps of the previous layer. And this is done using a learnable filter. And the next is the application of an activation function which applies pointwise to the output of the convolution. So the affine map is what the convolution produces, which is obtained by scanning the previous layer with a filter. And the activation map is obtained by applying something like a sigmoid or a ReLU or any other kind of activation pointwise to the output of the affine map. So here's what it would look like. All of the previous layer planes are going to contribute to the computation of the affine map. And each affine map produces the corresponding activation map. This clear? Any questions? Any questions? Right. So let's see how this works, okay? Let's actually look at the activation, how the convolution works. Now, again, observe that when I'm computing the convolution over here, I'm actually simultaneously looking at all of the maps of the previous layer. But to understand how it works, I'm going to focus on the contribution of just one map over here. So let's see how that brown map to the left would contribute to the activations in the map, affine map highlighted in yellow. So top left, right? So let's see what this would be like. So let's assume that that brown activation, the brown map shown, which is one of the maps from the previous layer, is given by this green picture, right? And what we are trying to compute is the yellow map that it contributes to. Now, corresponding to that, there is going to be a filter. So let's say this guy is looking at a 3x3 region of these maps. So then the filter is going to have a 3x3 set of elements. In my example, all of the elements are binary because I stole this example from the web. And now a filter, an affine map, has a bunch of weights. It also has a bias. Don't forget the bias. I'm just going to assume that the bias is 0 over here. So here's what it would look like. This green picture is the output map from the previous layer. The orange shows you the filter. And this white box to the right is the corresponding output affine map shown in yellow, right? And I'm showing you how it is computed. So I would place this filter over here on top of this image of the previous layer map starting at the top left corner. So the previous layer map has a bunch of values. The filter has a bunch of values. I'm going to perform a component-wise product of the filter values shown in red with the map values shown in black. And then I sum up the lot. And then I finally sum the bias. And that's going to give me a result. And that's going to be the result for the affine map at the top left corner of the output affine map. And then I can slide the filter forward one step at a time and repeat this operation at each location. And that is going to compute the final output affine map. This animation makes sense? I stole it, it better be good, right? So,
Professor?
yeah.
Just to continue the analogy from like the T cell and C cell. So whereas in the earlier model, the C cell operation on the S cells was deterministic, this is, I mean, now we have like a C cell that
No,
doesn't.
this is an S cell. This is not a C cell. This is an S cell.
Okay.
Okay,
Okay.
right? So I've just shown you what happened so far before one of those, how one of the orange maps, brown maps, contributes to the yellow map. But then in reality, each affine map is computed by looking at all of the previous layer maps, right? So if this here represents the entire set of maps from the previous layer, then in order to compute any given output map, I'm going to have a filter where the filter has as many, I'm calling this planes, or I can call this channels, which is the common terminology, as the number of channels in the output layer, or in the output of the previous layer. So here, my previous layer has at least 3 channels. There's a triple dot showing you that there are more. So correspondingly, the filter, which I've figured is going to be looking at a 3 cross 3 region, is going to have one 3 cross 3 arrangement of weights for every channel of the previous layer. Basically, what we're saying is that there's going to be one 3 cross 3 for this one for this one for this one. That's what the picture to the right shows. And there's no requirement that all of these values are identical. As the color code shows, the numbers can all be different. And so I place the filter on the top left corner, like so. And now I'm going to perform a component-wise product over all of the colored numbers and then sum them up. And that's going to give me the top left corner of the output affine map. Then I'd slide the filter one step forward, and that's going to give me the next position of the output affine map. And I can repeat this operation again and again to compute the entire output affine map. That makes sense to everyone? I spent a lot of time on this animation, so. Yes or no? We're going to use it, right? But this is one filter, and it's going to generate one output affine map. If I want to generate a second again, remember I have multiple of these guys over here, right? So what would I need to generate the second one? A completely different filter. And now I'm going to be scanning the inputs with the second filter to generate the second output map. And so I'm going to have as many filters as the number of output maps. And each filter is going to have as many channels as the number of input channels to this convolution, right? I can also view the entire thing differently. Instead of drawing all of these planes one on top of the other, I can stack them up in the form of a cube, in which case my filter is also going to be a cube. And so I can think of this entire operation as just placing this cube at the top left corner of the stacked arrangement of S-planes. And then the actual computation I'm performing is an inner product, which is to say, I take an element-wise product of all the values within the filter and the corresponding values of the channel in each plane. I do this for all the planes and sum over all of the planes, and that's going to give me one output. And then I can just slide my filter to generate my entire output. Did this make sense? The visualization? Any questions? Any questions? Okay. So this is what is really happening over here. Now, there are some little engineering aspects that you would have to worry about in doing this. The way I've pictured it, it would appear to you that there are going to be as many output. The size of the output is going to be the same as the size of the input, which is not the case. And that's because your filter has some spatial expanse. So here, When I place the filter to the top left, that filter is taking up 3 columns, right? I can only step to the right twice more before I fall off the edge of the input. So in general, if my input is n cross n, so if this is n, and if my filter is some k, then how many are left after I place the filter in the first position? N minus k. So I have n minus k steps I can take in addition to the first position, right? So the total number of outputs is going to be one output for being here, 1, plus the remaining n minus k steps that I can take, right? And this would happen in each direction. So if the image is 5 cross 5 and the filter is 3 cross 3, what is the size we can generate? The initial 3 is going to produce one output, and then there are 2 more steps I can take, which is why the output is 3 cross 3 over here, right? Or in general, if the input is n cross n and the filter is m cross m, then the output is going to be n minus m plus 1 on each side. Does that make sense? Right. So this, although it's proportional in some sense, the output is proportional to the input, you're losing some stuff at the boundary. And often we don't like this. We want the output to be the same size as the input. If that's what you want, what would you do? You can just pad zeros, right? I can just put a bunch of zeros distributed symmetrically around the input. And now I've got it. And how many zeros would I add?
N plus a minus n.
So here's what I would add, right? I started off at n. I ended up with n minus k plus 1. So the difference is the difference between these two, which is, what is that going to be? K minus 1, right? This is how many rows I'm losing. So those are how many rows of zeros and columns of zeros I'm going to pad the input with. And then and then the output would be the same size as the input, right? So easy. We figured out how to perform the convolution. The next step is for us to apply an activation. And so to apply an activation, we just pointwise multiply, pass each value through some activation function. In the original CNN, these were sigmoids. And sigmoids, because sigmoids approximate the threshold function. These days you use a ReLU because we find that it works better for the reasons that we saw in the second lecture, right? And I just have pseudocode. Let's get the pseudocode. So convolution summary. Convolution layers scan the input. Again, this pseudocode is exactly the same pseudocode that I showed you in the last class. We're just arriving at it from a different perspective, which is, as a model of mammalian vision. And that's where CNNs originally came from. So convolutional layers scan the input using a bank of filters. A filter is just a neuron in a scanning layer. Again, they call them filters, terminology. Each filter jointly scans the maps in the previous layer to produce an output affine map. And you get as many output affine maps as the number of filters. Then we may have to pad the edges of the input maps to ensure that the output maps are the same size as the input maps. If not, the convolution is going to lose some rows and columns. And the output of the convolution is finally put through an activation, which I've not mentioned on this summary, to get you the final activation map, right? There was another component to this model, pooling. Pooling was the same as the C cells, right? And now, again, remember that when we were computing the S planes, each S cell was looking at all of the planes, all of the maps in the previous layer. In the case of the C, that is not the case. So, may I know your name there? You don't have your name tag? Do you want to go wash your face?
Yeah, probably.
Yes, please do. Right. Thank you. So, he has his coffee, but still it's too early in the morning. It's still dark. Okay. So what are these pooling layers? in the pooling layers, remember, we mentioned this briefly in the last class. Each S cell is composing patterns from the sub-patterns seen by the previous layer. So it might say, I've got to put a little bit of a petal, a little bit of a sepal, a little bit of a stamen, and this is going to look like a part of a flower. But then, if the petal moves just by 1 pixel, it doesn't suddenly become a knot of flower, right? And so we want to introduce jitter invariance. And so what the pooling layer, which is the C cell, does is to look at regions of the input and just pick the largest value. So if that region had 3, 1, 4, and 6, the largest value is 6, so it's just going to output a 6. And now it's done with that block, so it's going to step forward. But then computationally, for our purpose, it's always convenient to think of these things as moving 1 step at a time. In practice, when we perform pooling, you'd be taking larger steps because you're done with a block, you're moving on to the next block. But I will explain why this, thinking of it in terms of blocks and strides greater than 1 can become a tedious thing, and why it's simpler to think of this as performing its operations with a stride of 1. So that's what would be happening over here. At each position, just be picking the largest value to compute the output. So here I have pseudocode for it. You'd be going through you'd be within any layer for each of the output maps from the convolution. You'd be scanning it left to right, top to bottom. At each position, you're looking at a window of the values, and you're picking the largest one. So you're scanning it. So see how the code is written. You first find the position of the largest value, and then copy the value at that position. You could just run a max operation and have the same outcome, but it's for reasons that we will get to in the next class, it is better for us to actually first find out the location of the maximum, which is what is stored in this variable called PIDX, and then copy the value at the PIDX into 1. That's what this max pooling does. You can have other forms of pooling. You can have mean pooling, where you compute the mean of these 4 values as you slide forward. And so here, in this case, it's much simpler. You don't have to find the location of the maximum. You just compute the mean of all of the terms of the window that you're looking at. And this is going to be performed separately for each of the maps. Remember, this is the equivalent of the C-place, right? You can have other kinds of pooling. There were things like p-norm pooling, which compute a different function of the inputs. And people even propose that we can actually learn a network that does something better than either max or any kind of norm, but it's just adding complexity for no really great reason. So pooling layers scan the input using a pooling operation, selecting the max from the k cross k block of input. Each pooling filter scans an individual map computed from the convolution, and this produces a pooled map. And so you get as many output maps of the pooling layer as the number of input maps, right? Whereas in the convolution, the number of output maps doesn't have any dependence on the number of input maps. It depends only on the number of filters. If you add filters, you get more maps. Whereas in pooling, because each pooling operation is performed on 1 map, the number of output maps and input maps must be the same. And for pooling, you generally don't pad the edges with zeros because you could just end up losing information. And so here are all the steps we've considered so far. Convolution layers and pooling layers. There's the MLP at the end, but we're familiar with MLPs. But there are a couple of other operations that we must think of. And these operations change the size of the output. So the first operation is downsampling. If I start off with a 10 cross 10 map, and if I want to shrink the size of the map by a factor of 2, what is the simplest thing I can do? Anyone?
Remove the values like.
I can just drop terms, right? So here's what I will do. I start off in this case with a 6 cross 6 map. I want to shrink it to a 3 cross 3 map. So guess what? I'm dropping every second term. That's about it. So here's the first position, then I drop this, the blacked out region. Then here's the second value, I'm copying it, then I'm dropping the next one, and so on. And so this is downsampling. You're just dropping every S minus 1 out of every values in every direction. They're downsampling by a factor of S. This is a very easy operation. Here's the code, right? Trivial. So reducing the size of a map is always performed by downsampling. Downsampling is always performed by just dropping things. Now, in practice, convolution can be followed by downsampling. Pooling can also be followed by downsampling. And if you were actually implementing this in code, you're not actually going to perform the convolution with a stride of 1 and then downsample by a factor S. Instead, what you would actually do is to perform convolution with a stride. So here, for example, you might go like so if you want a stride of 2. And now we're just going to, reduce the output size by a factor of 2. So also with pooling, right? So if the input is n cross n and filters are m cross m, earlier we just had n minus m plus 1. If you factor in a stride, the output size is going to be n minus m over s plus 1. So why am I explicitly teaching you about the downsampling layer instead of just saying you can convolve with a stride or pool with a stride? We will get to this when we talk about back propagation in the next class. But it's very important to think about it as think about downsampling as a separate operation, right? So in practice, again, you'd just be performing your convolution with a stride. Every time you move forward, you're going to move forward by a stride. And you can do the same thing with pooling, right? You can pool with a stride of 1 and then downsample by some factor, or you can pool with a stride. And pooling is almost always performed with a stride, which is why the pooling layers were also originally just called downsampling layers. They are not. A real downsampling layer is one which just drops S minus 1 out of every S layers, columns, and S minus 1 out of every S rows, okay? That makes sense to everyone? Okay, if I can shrink the image, what is the other thing I can do?
Expand.
I can expand, right? How would I expand? Can someone say that aloud? Add average values. Theo, how?
Make the 6 into 4 6.
Make the 6 into 4 6s. Can you give me something simpler I can do?
Add zeros.
Okay, so this is what I can do. This is the most trivial way of increasing the size of something, right? And so this is what an upsampling layer does. You literally take whatever you got and stretch it out, and you leave holes in the middle, and that's your upsampling layer. And so to upsample by a factor of s, you're going to add s minus 1 zeros between columns and s minus 1 zeros between rows. Make sense? Very trivial, right? Nothing fancy. No averaging, no computing magical things. Just put in zeros. So easy. And let the network figure out what to do with those things in the middle. So an upsampling or dilation layer simply introduces s minus 1 rows and columns for every map in the layer, effectively increasing the size of the map by a factor s in every direction. And this is used to explicitly increase the map size by some uniform factor. Now, here's what happened. When we were speaking of downsampling, downsampling followed an operation. Downsampling followed pooling. Downsampling followed convolution. Upsampling, this cannot be the last operation, because if you make it the last operation, you're just leaving the image with a bunch of zeros, right? So the upsampling always precedes an operation. And what kind of operation do you think it would precede? Does it make sense for upsampling to precede a pooling layer? You're just going to be throwing away stuff and putting in bunches of zeros, right? And so upsampling is always followed by a convolution layer. And so therefore it doesn't make any sense for this to be the final layer of a CNN. You're just introducing a bunch of zeros. What do you expect the convolution to do over here? You expect the convolution to figure out how to fill in those zeroed out values with something meaningful. You are not taking the responsibility yourself. The network will learn what is the best thing to do to fill those values with, right? So upsampling here, I can just initially allocate something which is the upsample size and then copy values over into the non-zero locations, right? So in terminology, very often they speak of upsampling followed by convolution as convolution with a fractional stride. So when I say convolution with a stride of 0.5, what this means is that first you increase the size by a factor of 2 by inserting zeros, and then you perform the convolution. Make sense to everybody? Questions? Okay.
Are you often just doing the upsampling to like make the math nice, or do you actually like get more information when you apply the filter because it's only looking at like 1 pixel or whatever it is around your filter?
So, okay, let me go back to a very important point that I missed. Thank you. So, and this is only indirectly related to what you just asked, but I will get to your answer, and maybe I'll spend a couple of minutes on this. What are the operations we just spoke of? Let's think of an input. Let's say I have a 100 cross 100 image, right? And then I perform some convolutions on it. So maybe I got, so I'm going to get 100 cross 100 over here, and 100 cross 100 over here, and 100 cross 100 over here. This is going to be the result of my convolution, right? 1 per filter. Is this going to be a lossy process? Am I losing information? No? Yes? In principle, it doesn't have to be, right? The number of values I'm outputting in this step is the same, at least the same as the number of inputs I've got. And so there doesn't need to be any loss of information, right? But then suppose I have a pooling layer, and the pooling layer has a stride of 10, just to be dramatic, right? This output is going to be 10 cross 10. Do we have loss of information here?
Yes.
I've thrown away whole bunches of values, right? So how do I make sure that I don't lose information? Anyone? I need to have as many numbers as I have here, which means that this set must have as many numbers as I have here, right? Every time I downsample, I'm losing stuff. How can I compensate for that? Add more boxes, right? And so the more layers I've got, the more filters I've got, the more values I'm copying over, and then the subsequent pooling and downsampling is not necessarily going to lose information, right? And so what will happen here is, that making sense to all of you guys? Right? And so if I start off in your color image, we'll get to that. You are going to have an image of some kind, and typically if it's an RGB image, you'd have 3 images, 3 channels, right? And so after the first convolution and pooling, you're going to end up using still the cuboidal representation that I showed earlier. You're going to end up with something that's where the face is smaller. So how do I compensate for the face being smaller? Add depth, increase the number of channels, right? And so as I keep going through the layers, these things are going to get smaller and smaller in size, but then I'm going to be getting deeper and deeper so that I don't lose information. That make sense?
But isn't pooling like inherently lossy because you're combining?
Yes, but I'm compensating for it by adding more channels.
But the network's just interpolating. Like you're not actually using it.
So here's the thing. So when I'm losing some information over here.
Yeah.
I'm hoping that some of that information I'm lost ends up in this other guy.
Okay.
Right? And so by adding the number of channels, I maintain the ability to retain all the information because the total number of values that you've got at the end stays the same. If you didn't, you'd definitely lose information. Okay, that didn't answer your question, right? So what happens next? Suppose, now let's say I was building a network which starts off by analyzing pictures, and ends up, the outcome must also be a picture, but just modified. So does this look like a picture? This was 100 cross 100, maybe this is 5 cross 5, but then a whole bunch of channels. Does this look like a picture? It does not, right? So the next thing I would do is to make it 10 cross 10 by introducing, or whatever, by introducing a whole bunch of zeros. And then when you fill it up with convolution, what does convolution do? Is it just looking at the local image? It's looking at everything down the column, right? And so it's using using the inverse of the principle that we had over here, that by adding columns, I can still retain information. Now I'm using information in those columns to fill in the holes. That answer your question? Right, so it's not just merely interpolating locally, you're looking at everything. Questions? Yes.
Yeah, sorry, can you explain that one more time? I don't understand.
Okay, so here's what happened when we were going forward. When we were going forward, in order to account for the fact that we are losing information in individual channels, we added more channels. So if this has 10,000 values, so long as I have 10,000 values after pooling, I have some hope of retaining all the information over here. Yeah.
Okay. So we're adding channels. We want to add channels in the pooling layer. We can do that by adding channels in
You cannot add channels in the pooling layer. So you're going to be adding channels on the
convolution.
convolution, and then the pooling happens, right? So this is actually planning for the future.
Yeah. Okay.
And then you've lost stuff, but if you train it just right, you're still going to retain the information. Yeah.
Is there a requirement for like how many channels you have to add so that
If you want a guarantee that you will not, or if you want a necessary but not sufficient condition that you won't lose information, then you want to make sure that the number of outputs you get after pooling is at least as much as the number of inputs that went into the entire convolution layer, right? You can add more channels, just to be safe. But sometimes you really want to lose information. If you're performing classification, you want to get rid of CRUD. So there's, it's more complex than that, but this is the general idea, right?
I didn't get how the how the convolution after the upsampling get the information from the initial layer.
So here's what happened, right? So when I pooled down over here, I was able to afford to lose information here because this guy here captured whatever I lost up there. You can think of it, for instance, as maybe some channel down there which is just shifted by 1, right? I can always guarantee that happens, that there's a second channel which is just a shifted value of the guy up there. So, when you pull them down, you have all the values, right? So now if I'm going back from this, I'm just expanding it out to fill zeros. What are the values I would be filling over here? The values that I got from down there, right? So to give you an idea, suppose I had something very naive, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, then I could be considering composing 2 channels, 1, some nonsense, 3, some nonsense. I'm just putting, right, 5, something, 7, something. And the second one could be just these values. So now I have 2 channels, and together they're retaining all the information. If I downsample each of them individually, each of the output channels looks smaller, but the complete set of values is retained. That make sense? Right? So when I expand them out, I want to copy values from here up there. Did that make sense? Yeah. So which is why you want to increase the number of channels, and upsampling will still reconstruct things by copying things from other channels. Yes.
When you add channels in the convolution layer, you're basically creating information.
There's no such thing as creating information. There is the data processing inequality in the information theory, which says you cannot create information. You're just spreading it out over more channels.
But then you have more stuff in the convolution.
Yeah, you're just adding, it's like adding many more functions, right? So you're extracting more features, but you're never really adding information. You're just sort of making them more apparent by transforming the data. Yeah. You cannot add information. That's just a fact.
Perfect.
When we use the upsampling layers, what values do we use for initializing?
When you're upsampling, you're just adding a bunch of zeros. Then there's a convolution layer, right? So there's no initialization. Okay. Let me continue, right? So map sizes can be changed by downsampling or upsampling. Downsampling, drop S minus 1 of S rows and columns. Upsampling, insert S minus 1 rows and columns, right? And again, this when you go forward, you would be downsampling. So if you thought of the input as a cube, the face of the cube is going to get smaller, but the depth is going to keep increasing. And then when you're going back upsampling, you're going to be doing the reverse. You're increasing the face of the cube and reducing the depth, and you would not have lost information in the best case, right? So downsampling typically follows convolution or pooling. Upsampling occurs before convolution. Questions? You ladies at the back, any questions? Sure. Okay. So the story so far, convolutional neural networks are supervised versions of computational models of mammalian vision. They include convolutional layers comprising learned filters that scan the outputs of the previous layer, and pooling layers that vote over groups of outputs from the convolution layer in some manner. Convolution can change the size of the output due to edge effects. So this can be controlled via zero padding. Pool layers may perform max, p-norms, means, or they can be learned. Resampling layers increase or decrease the size of the map. Downsampling can be merged with the preceding operation by scanning with a stride greater than 1. Upsampling must be followed by convolution, right? Everything we've seen so far. So here's a poll. Is this not showing up?
It should be multiple choice and it's selected.
Okay, all right. So if we've set up the poll wrong, that's too bad. But somebody on Zoom, can you tell me which of the first 4 statements is true for question 1 on Zoom? Anyone on Zoom?
The first one.
The first one, upsampling by S introduces S minus 1 zeros between adjacent rows and columns. What about the second one?
It's true.
Is the second one true? Are upsampling layers followed by pooling layers?
No. It's false.
Are they followed by convolution layers? Yes. Can they be combined with convolution? Upsampling layers must be followed by convolution layers, right? Otherwise, you're just going to be left with a bunch of zeros. And then upsampling layers can be combined with convolution or pooling layers before them into a single operation with a fractional stride. That's the terminology. They just call it operations with a fractional stride, but not with the stuff before them, is the stuff after them, right? So what about the downsampling layers? Downsampling by S replaces every S row and column with zeros. Is that true? False, right? So what about the next statement? Downsampling by S deletes S minus 1 consecutive rows and columns. True, right? They're usually merged with convolution or pooling layers after them. True or false? True or false? Guys, everybody say, just shout your answer out loud. Okay, I'm expecting everyone to say something. If I hear chaos, I've lost you. If all of you are giving the same wrong answer, I'm happy. If all of you are give me the same right answer, I'm happier still. Okay, go ahead. 1, 2, 3. True or false? Okay, we heard noise, right? They are not merged with the layers after them. This is downsampling, right? Downsampling is merged with the layer before it. It's about the operation with a stride. Correct. So, questions? No. Okay, let me continue, right? So let's put all of these together in the last 10 minutes of the class in a typical image processing, image classification task. Here I'm going to assume max pooling. You typically start with a color image, which can be zapped down to a gray color, a gray shade image, or more likely you just retain the red, green, and blue separately. So the red, green, and blue, here is the input, 3 pictures, which I can stack into a cube. So now the input itself has 3 channels, the R, the G, and the B. It's not just a single plane, right? And then the first thing I would do is to come up with a bunch of filters. I have to decide the face of the filter, some L cross L. And each filter has a depth 3 because the input has 3 channels, right? And so what is the number of filters? Typically, the number of filters we use is a power of 2. Now, why would this be a power of 2? What would be a reasonable? Okay, based on what I have told you so far, just by looking at these, if I told you that I'm going to use 4 filters, what can you tell me is going to happen next? You were saying something?
You're gonna downsample.
I'm going to downsample by a factor of 2, right? So this makes that way I make sure that I have all the information, that I retain all the information. Having 2 filters makes no sense if you intend to downsample, but having 4 makes sense. So always it's going to be some 4 or some multiple, right, in those cases. And the filter sizes are typically 3 cross 5 cross 5, 3 cross 3, or even. These are small enough to capture fine, detailed features for scaled down images. What is a 1 cross 1 filter? You will encounter this again and again. And believe it or not, you have already encountered it in class. What is a 1 cross 1 filter? Essentially an MLP. So what was that? Have we seen this in class? What was a 1 cross 1 filter? We've seen this in class. In the last class, before we began speaking of distributed scans, we spoke of non-distributed scans, right? And when I had a non-distributed scan, what did I do? Each neuron produced a map, and the next layer neuron looked at only one neuron from each of these maps. Remember? What was that? That's just, you're taking all of these 3 guys and generating one output. That's your 1 cross 1 filter. It's a scanning with a single perceptron. That makes sense, right? Recall this? That's the non-distributed version of the scan, right? So it's simply a perceptron that operates over the depth of the stack of inputs. It's a non-distributed layer of the scanning NLP. Okay, and so better notation, filters are typically 5 cross 5. This cross 3 is to say the depth of the filter itself, how many channels the filter had.
Sorry, could I ask a quick question?
Yeah.
If you have 4 filters and 3 input channels, does that mean that the output will produce 4 channels?
If I have 4 filters, the output will be 4 channels.
So you're increasing the channel because the input is 3 channels, right?
Yes.
Okay.
Right. So over here, the number of parameters you're going to choose are, the number of filters, the size of the filter, the stride of the filter, and so you're going to have as many output channels as the number of filters, which I can stack up, right? So I'm going to skip some of the numbers over here. You can just check them up. I can perform pooling on each of these guys. Now here is something else that's important. We know exactly how to perform convolution and compute the output. At each position, you're computing the affine value Z, then you pass the affine value Z through an activation. So that it's a 2-step process. You're going to be computing an affine value at each location for each channel. The affine value is going to be summing over the entire filter. And then you have a bias. And then you pass that through an activation function, which is whatever you choose it to be. Then subsequently, you're performing pooling. And how did we perform pooling? We have a window size. You have one pooled output per convolution channel, right? And we choose a window size and we perform whatever pooling operation we've chosen. In my example, it's max, and perform the pooling operation over it, right? And so that's going to give you this reduced map size, because typically pooling is performed with a stride greater than 1, because it makes sense. And so the output of pooling is going to be the max of the values within the window. But you never just directly take the max. Here's what you would do. So here the parameters to choose are going to be the size of the pooling block and the stride, and choice. Is it max pooling or mean pooling? I'm assuming max. But here's the actual operation you'd perform. You don't just pick the max value of this window. You do this in a two-step process. In the first step, you identify the location of this max value. That's what I'm storing in the variable p. In the second step, you copy the value at this max position over. Can anybody guess why I would be doing this?
Because region is important.
Because?
Region where that pattern.
Not just the region, right? Why am I retaining the position of the max?
Back propagation.
During back propagation, I need to know where the derivative will go, right? Otherwise, I have no idea. I picked up a max. I know, for example, if I take a max of 4 values, the only value that I can perturb and change the output is the largest value. The rest of them must have a derivative of 0, right? And if I don't retain information about where I got the max value from, then I cannot pass the derivative backwards. And so that's going to give me some kind of an output. And a jargon, the filters are often called kernels. The number of individual filters is basically the number of planes, which you often call channels. And so the number of filters is the number of output channels. The number of planes that you're working on, the filters work on are the number of input channels. And then you'd have a second layer of convolution with its own bunch of filters, which would generate a bunch of output channels, its own pooling, and the parameters you must choose for it, its own pooling, and so on. And then finally, an MLP. So this is what the entire operation is going to look like, right? So each convolution layer with stride 1 typically maintains the size of the image if you have 0 padding. If you don't have 0 padding, you lose a little at the edges. Each convolution layer will usually increase the number of maps, the number of channels. And the reason for this is that you're going to lose information otherwise if you have any kind of pooling with downsampling, right? Each pooling layer with stride D decreases the size of the maps by a factor of D on each side, and filters within a layer are all typically the same size, right? Although the size of the filters may vary from layer to layer. And in general, the number of convolutional filters is going to increase from layer to layer for the reason that I just mentioned, okay? So the parameters to choose would be the number of filters, the size of the filters, the kind of pooling, and so on. So all that is fine. Now here's a question I'm asking all of you. What is the relationship between the number of channels in the output of a convolution layer and the number of neurons in the corresponding scanning MLP? Anybody want to answer this?
They are the same.
They're the same thing, right? So they are the same. And we had this digit classification example that we saw earlier. But before that, so what we will look at next week, by the way, guys, our classes next week are going to be on Zoom. I will not be in town. So I will not be in town for the rest of for all of October. So all classes in October will be over Zoom. So here's how we're going to perform training. It's just as in the case of a regular MLP. The only difference is in the shared parameter structure of the network. So you'd have examples of data, images, and their class labels. In the forward pass, you're going to pass the data through the network until they get to the MLP, and then you have the output of the MLP. And then you're going to compute derivatives at the output. You're going to compute a divergence at the output, and the divergence is going to be propagated backwards. And the derivatives of the divergence are going to be propagated backward. As they go back through the convolution layers, you're going to keep track of this business of shared parameters to make sure that any update at one location reflects 2 updates at all locations. So you would do this by simply updating the filters directly. So we'll go through all the rules of all of this, how back propagation is performed in the next week. Any questions? Questions? No? Thank you.